Hello, everyone, and welcome to another wonderful day of physical chemistry. So, today we are going to take what we learned last time about rotation in two dimensions and apply it to uh, molecular rotation in three dimensions. And along the way, we're going to introduce Legendrian polynomials. So, what we can do is take our knowledge of the rigid rotor from last time and try and expand it. So now we're allowing rotations in three separate directions. So just like last time, phi is going to represent rotation in about the z-axis. So this can go from 0 to 2 pi. However, the new dimension that we're now going to be introducing is theta, which can go from 0 to pi. So this is essentially how much along the z-axis uh, how far up and down we along the z-axis we are now pointing. So what we can do is first by starting generating a generalizable three-dimensional Hamiltonian. So for any three-dimensional system, the kinetic energy can be provided using the Hamiltonian form of our good old classic negative h bar squared over twice the mass. And then we introduce this new term, which is called the Laplacian. So the Laplacian is essentially a fun mathematical term, which means I'm taking the sum of the second derivatives in every single direction. So this is actually an idea that we've used before. We're just giving a new condensed notation for it. So not too surprisingly, you'll see me pull out the Laplacian every once in a while. And this is essentially a way of me talking about looking at the kinetic energy or movement in a three-dimensional space. However, the unfortunate part is that, as we saw last time, Cartesian coordinates kind of suck. So we need something that's a little bit less cumbersome to move. And this is really where our spherical coordinates are going to come into play. So last time we got a little bit lucky. We only needed to use cylindrical coordinates. It turns out the conversion from a Cartesian Laplacian to a spherical Laplacian is a little bit annoying because it turns out it generates a lot of terms. So not too surprising, we can actually split up the derivatives into three sections. So the first part is going to be a derivative just with respect to r. So this is going to be a good old second derivative with a prefactor of 1 over r. The second term is going to be a second derivative with respect to theta. So this is again movement about the z-axis or phi. And then the last one is going to be a kind of messier second derivative with respect to theta. So we have a normal first derivative with respect to theta, and then we need to bring in a sine theta and then do the second derivative with respect to that. So suffice to say, this isn't exactly one I'm going to be expecting you to do at the drop of a hat. This isn't a physics quantum mechanics class where I'm going to make you run difficult calc all day. But it is worth acknowledging that this is going to be going on in the background. However, we can go ahead and try and condense this equation a little bit more. And so one of the ways we're going to do this is by separating this equation out into radial parts, which is pretty much this first term, and then into angular components. So notice that we have a shared r squared as a prefactor in both of our angular components. We get to pull that out front. And then what we're left with is, well, let's be honest, still fairly messy. We have our theta dependencies, or phi dependencies, and our theta dependencies. And again, that ugly theta derivative. So what we do is we go ahead and take this combined derivative and we give it its own variable of delta squared. So delta squared is also known as the Legendrian. So a good way to think about the Legendrian is it's kind of the angular version of the Laplacian. So the Laplacian is a second derivative with respect to Cartesian directions. And again, you can reframe it into angular or into a spherical coordinate system. The Legendrian is more or less the second derivative just with respect to the angular portion. So if you're looking at changes in angular motion, angular kinetic energy, the Legendrian is really going to be where it's at. However, it is worth noting to turn it into a Laplacian, we do introduce this prefactor of 1 over r squared, and we also have to add in our radial second derivative. However, one of the nice things is that the Legendrian does give us a fairly condensed way of representing a general Hamiltonian for a rotating three-dimensional system. So we can take our general equation, which again is the kinetic energy for, gives us the kinetic energy for any three-dimensional system. We break it into this radial portion, which honestly, that doesn't look too bad. And then we use this angular portion, which again has a lot of similarity to what we've seen before. We have an h bar squared. We have 1 over twice mass times r squared. Wait a minute, I think I know that one. Because what we can do is now turn this into again a rigid rotor, but now a rigid spherical rotor. So this is also known as particle on a sphere. So we now have a fixed r, so that second derivative with respect to r goes away. And this mass times r squared is, congratulations, our moment of inertia comes back. Now, it is worth noting that as we go into a molecular system, that mass does again translate into reduced mass, and it gets a little bit messier for polyatomic systems, but that's next time. But what we've done is we've taken kind of a messier general Hamiltonian, and then for particle in the sphere, we've simplified it a little bit. So now it's just going to be in terms of good old Planck's constant, our moment of inertia, which we've played around with before, and okay, the Legendrian still isn't exactly going to be our best friend, because when expanded, this is still not the nicest equation we've ever worked with. However, what we're still going to be in need of is some eigenfunctions and some eigenvalues. So, turns out that this is actually a well-known set of equations, which was solved far before quantum mechanics. So, go for pure mathematicians. And this set of eigenvalues and eigenfunctions has a known set of solutions called the spherical harmonics. So the spherical harmonics are going to be the eigenfunctions of our Legendrian. However, one of the nice things, especially for us, is that we have a very pretty set of eigenvalues, where our eigenvalues are just going to be negative L times L plus 1. And this is going to hold as long as L is a real positive integer. So essentially, any values of 0, 1, 2, 3, 4, and so forth. So this gives us actually a nice set of eigenvalues, which is specifically nice. Is the reason we were doing this originally was to generate a Schrodinger equation for a rigid rotor. Yes, there are a lot of moving parts to this. However, once we have, in order to get the Schrodinger, all we need to do is add on this prefactor of h bar squared over 2 times the moment of inertia, which means our eigenvalue for the energy is actually not the worst one we've dealt with. It's just going to be h bar squared times the angular times the rotational quantum number times itself plus 1 over twice the moment of inertia. So this is more or less going to be our energy eigenvalues. However, this leaves us with the messier portion. This kind of makes sense in terms of energy values. But what does the system actually look like? So for that, we need to kind of examine our spherical harmonics. And part of the problem with this is the spherical harmonics don't exactly have a nice, simple pattern to them, but I can try and emphasize some of the important features. So one of the first things you should know is that the spherical harmonics have a dependency on 2 different quantum numbers. So first we have L, and this is the only quantum number that shows up in the energy. But it turns out that our good old friend M sub L also shows up here. So L is going to tell us a lot about the energy of the system, And as a consequence, just like with a particle in a box, L also tells us a lot of information about the total number of nodes present in the system. M sub L is going to tell us the same thing it did with the two-dimensional system. Most notably, it's going to tell us a lot about the angular momentum in the z direction. So it's going to tell us how much of the angular momentum is pointing straight up. So let's go ahead and try and decipher kind of what's happening with these spherical harmonics. So the simplest case is if I have an L of 0, this means I'm going to have an energy of 0. Gotta love that. This is our ground state system. Just like with an M sub L1, it means we have no rotational motion. And not too surprisingly, no rotational motion means that we have no nodes. No nodes whatsoever. All we're pretty much left with is a normalization constant. So this guarantees essentially a smooth particle density everywhere. And we really aren't having any movement, and any movement that does occur essentially is going to be random and chaotic enough. It doesn't actually have generate an angular momentum. Then when we go up to a value of L of 1, this means I'm now at my first excited state. So I am going to be generating an angular momentum, but now I have essentially a couple of options. And they're going to more or less devolve around to what direction is that angular momentum pointed. So if M sub L is 0, that means that none of the angular momentum is going to be pointed in the z direction. So this means that all of the angular momentum is going to happen in the happen to some extent in the z plane. It could be the xz plane where I'm going like this. It could be the yz plane where I'm now going in and out of the board, but still up and down as well. So in truth, you're going to find some combination of these two. But as a result, because I now have an excited state energy, L is going to give me a lot of information about the number of angular nodes. So here, my angular nodes are going to be 1. And that angular node is going to happen right around the middle. And you can see this with the spherical harmonic, because I will have a wave function of 0 at a cosine of pi, or sorry, a cosine of half pi. So essentially at the middle of the equation. So when theta equals pi halves, so at the middle of the sphere, at this point, equation goes to 0. I have an angular, I have a node in my wave function going right around the middle. Something a little bit more interesting happens if I have an M sub L of plus or minus 1. So again, as a reminder, M sub L of plus 1 is going to mean I'm going to have an angular momentum in the z direction. So I've got some sort of motion going in the xy plane, which is generating an angular momentum up. And again, plus 1 means that I'm rotating clockwise from underneath. So counterclockwise from above, use your right-hand rule. So I'm rotating in this direction. And as a result, our node does something kind of fun, because with a sine of theta as the prefactor, this means I have a node kind of right here at the top and bottom, which means I'm not going to find my particle up here at the top or up here at the bottom, which makes sense because it's going to be hard if I'm moving generally in the xy direction to end up too high. So I'm going to spend most of my time around the middle, very little around the top, very little around the bottom. But we also have another interesting feature here. We have a plus I phi. This is the same plus I phi we had with the two-dimensional particle. And the reason why is this imaginary motion means that I am moving solely in one direction. And this is kind of cool, because what happens with an M sub L in the net of a negative 1 is I have what generally looks like the same equation, except for instead of now moving clockwise, I'm moving counterclockwise. So I'm moving in the reverse direction. Still have a node at the top or bottom, but I'm having additional nodes in essentially the imaginary plane. So again, some kind of fun things happen when we're talking about these when m sub l is not equal to 1. And this is the reason why you'll notice that all of the graphs of our spherical harmonics are generally going to focus on m sub l equals 0 because they get a little bit messier trying to graph an imaginary plane. But we see a very similar fashion as we go to uh, an L of 2. Now I've got 2 nodes, so we can see this best when we have a value of m sub l of 0, because again, now I've got most of my motion happening up and down, so I've got 2 planes. And this is going to be generated by, again, this cosine phi, and now by subtracting a value of 1, it means that when I have a value of, say, pi halves, I'm still going to end up with a real value. It's going to be a negative value, but again, it's going to be real. So we're going to have positive, negative, a wave function in the middle, positive at the bottom. And again, mostly dominated by this cosine term. When we go to m sub l of plus or minus 1, again, this is going to give us imaginary motion. So we're going to then have a single node. We're going to have a node at the top, and then a node running straight through the middle when we have an m sub l plus 1. And again, we now have introduced some directional movement. And again, node at the top and bottom when we have an m sub l of plus 2. And again, increased directional movement. And all of this more or less gets ramped way up when we have an L of 3. So spherical harmonics are a little bit odd to kind of visually work with, but we'll try and play around with them a little bit more in class, and we'll have a lot more practice with them because it turns out if they look familiar, go ahead and bust out a table of atomic orbitals. We're going to see these guys again. So let's go ahead and try and see what we can do with some of these values. Work with a quick problem. So let's try and use our three-dimensional motion to try and determine the energy of a hydrogen atom moving around a stationary iodine atom. Again, bond, fixed distance. We're not going to include any vibrational motion. Now, because iodine is so heavy, I can consider it fixed and treat the reduced mass or effective mass as just the mass of the lighter atom. So using this, I can find my moment of inertia, mass of the hydrogen atom times the radius squared, to give me, again, a good moment of inertia. We can then transfer this into h bar squared over twice the moment of inertia. So this gives me a value of 78.3 joules per mole. Again, the actual value is just going to be joules per molecule. Don't forget, we can always use Avogadro's to scale up to a molar value because that's a little bit more comfortable for us chemists. We're going to let the physicists play with just sheer numbers of joules. Now, one of the reasons why this is important is because this prefactor is really what's going to control our energy levels in HI. So we're going to have a general separation of h bar squared over 2I. And then again, the actual location of the levels will be dictated by our angular quantum number, L. So if I have an L of 0, I've got no rotational motion, energy of 0. If I have my first rotational excited state, energy is now simply can be given as twice this separation because, again, L of 1, this becomes 2, this is 1, fairly straightforward. However, one of the things I do want to make note of is the degeneracy of this system, because we only have one m sub l value for this first state, so single degenerate. This state becomes triply degenerate because I can have an m sub l of +1, -1, or 0. Then when we go to an L of 2, well, now what we end up having is 2 plus 1, so this is 3 times 2, so 6. So 6 times this original separation value, roughly around about 500 joules per mole, about half a kilojoule. However, it's worth noting that this is now pentuply degenerate, as I can have an m sub l of -2, -1, 0, +1, or +2. So one of the important things to make note of is that as we go higher in energy, what we end up with is as we go higher in rotational motion, the system starts to move faster. We tend to see it becoming much harder to access those higher energy levels, but there's more of those energy levels to occupy. And we saw this a little bit last semester when looking at statistical mechanics, in that you tend to hit kind of uh, a peak occupied energy level somewhere in between about uh, 2 to 6, depending on the mass of your system and the temperature that you're working at. However, this is kind of an important, useful thing to keep in mind. However, one of the other things I want to make note of is that it's possible to not only just determine the energy of the system, or even the angular momentum in the z direction using the two-dimensional operators. We can also determine the total angular momentum in 3 full dimensions. And we can use this via a set of relations we've already built up. So we now know that we can get the energy of a rotational system in terms of the rotational quantum numbers. But it's also possible to get it in terms of the total angular momentum. Again, as an analogy to Cartesian motion, energy is momentum squared over twice the mass. Now it's angular momentum squared over twice the moment of inertia. So we can use this to then solve for our total angular momentum as simply the square root of twice the moment of inertia times the kinetic energy of rotation. And again, using this, well, if I had multiply my energy times 2I, all I'm left with is an h bar squared times my quantum numbers. Well, h bar squared then can be pulled out front as h bar, and we're left with essentially Planck's constant times the square root of our quantum number portion of the equation. Now, one of the reasons I want to do this is to actually convey some very important parts about motion. First of all, one of the things you'll notice is that total angular momentum will only ever be positive, because my L has to be positive and it's sent through a square root. So total angular momentum is only going to convey a magnitude of angular momentum. It conveys no information about direction. So I don't know whether I'm going forwards, backwards, up, down, side to side. I know nothing. However, I do have a general feel as to how fast my total angular momentum, which means I do actually have some information about total speed. But again, speed, no direction to the movement. In order to get any directional information, we actually need to take a step back to our two-dimensional operators. But the issue is that now we have, instead of just our good old JZ with the angular momentum about the z-axis, since I can move in the z direction, I can move in the yz direction and have angular momentum in the x-axis, or I can move in the xz direction and have angular momentum in the y direction. So this gets a little bit messy. However, we are to a certain extent saved by the fact we already solved a two-dimensional system. So we can actually apply their angular momentum in the z direction, again, same operator as before, to our spherical harmonics. And it's going to produce the same eigenvalues we had before. Our m sub L value times our h bar. So again, we're going to get the same sort of angular momentum in the z direction as we did with the two-dimensional rotation rigid rotor. But I do want to actually emphasize kind of an interesting feature. So let's work a case where I have an L of 1. Well, if I have an L of 1, I can have an m sub L of plus 1. So if I have an L of 1 and m sub L plus 1, then my angular momentum in the z direction is h bar, and my total angular momentum is square root of 2 times h bar. So about 1.2, 1.3 times h bar. I know that one of that is pointed in the z direction. So most of my motion is occurring in that XY plane, but a little bit of it is pointing in that Z direction. Or is it moving in the Z direction? But what direction is it pointed in? Is it moving the XY, XZ? Is it moving in the YZ? Where is it going? So here we run into kind of a pesky issue. We can try and determine our angular momentum in the X or Y direction in a very similar fashion that we did for the Z. However, here we run into a very pesky problem. It turns out that the angular momentum in the X, the Y, and the Z direction form a set of complementary operators. Oops. And if you remember back to our lecture on the Schrodinger equation and commutators, if I have a commutator that is not equal to 0, this means that the equations form a complementary set, which means if I know one, I can't know the other. However, it is worth noting there are going to be a couple of exceptions to this, because we'll note that the complementary set of the X and the Y angular momentum gives us an equation in terms of the Z angular momentum. So it turns out the only way I can know something about the X or Y is if I have 0 angular momentum in the Z direction. At that point, we can start to get some information. But again, it's worth noting, not much. So by convention, we can only know angular momentum in one of the 3 directions. And at this point, it's pretty much by convention, we choose that if we only know information about one direction, we use the Z. However, it is worth noting that all of the same equations could be applied to the X or Y. However, our integrals wouldn't be quite as simple. So in general, we're going to choose to get all of our information about the Z direction. And again, it is worth noting, the more I know about the angular momentum in the Z direction, the more precisely I know it, the less I know about the other 2. So this means that I may know how much of the angular momentum is moving in the Z direction, but this just gives me no information. I know I've got 0.3 h bar of angular momentum in one of these 2 directions, but there is actually no way for me to know which direction it is. So we can only know one of them perfectly at a time, and we just choose by convention to use the JZ. However, it is worth noting we can actually relate our directional momentum in the X, Y, and Z direction to our total angular momentum. So again, if I do perfectly know my Z direction, I do know what the sum of the other 2 has to be. I might not be able to isolate it just down to one term or the other, but I at least know that the other 2 have to sum to describe the remainder. However, one of the things I kind of want to do is think about what this angular momentum term, what these angular momentum terms look like in terms of the actual operators. So let's go ahead and work an analogy where I have an L of 2. So I can have an M sub L of anywhere from +2 to -2. So if I have an M sub L of +2, what this means is that I know that most of my angular momentum is pointed in the Z direction. So most of my motion is going in the XY plane. But the problem is that some of it is always going to be in the Z direction. I can't completely get rid of that Z direction. So what ends up happening is I've got a little bit of that point in the Z direction, and it kind of precesses. So my angular momentum is always going to be pointed somewhere in this definite loop, generally pointing up. And this means most of my density is going to be kind of isolated towards the middle. As M sub L goes lower, I've got less of it pointed in the Z direction. I've got more motion in the Z direction as the angular momentum increasingly points in the general XY plane. However, I have no information of whether it's going to be pointing in the X or the Y because it's spending more or less equal time pointing in all of them. till you get to the point of an m sub l of 0. At this point, I've got no angular momentum whatsoever pointing in the z direction. All of my motion is happening up and down, no movement in the z direction. And at which point I know that all of that full angular momentum, all of that uh, 6 h bar angular momentum is pointed in the xy plane. But I've got no idea whether it's in the x, y, or anything in between, because it's all kind of constantly moving around. I know it's moving up and down, but I have no information about the other directions. And that's kind of the most that we can get. So again, this is really where Heisenberg truly starts to shine its ugly head. I get some idea of motion. I can identify total motion and motion in one direction, but the other two directions will forever remain unknown to me. And this is something we pretty much have to deal with in reality. So next time, we're going to take some of these ideas of three-dimensional angular motion and slowly build up how we can do spectroscopy in a rotational frame. Until then, take care.